Hello, everybody. This is Pallavi Pujar from Biotecnika. I hope you are enjoying all the revision series of chemistry and biology of NEET. All right. So now I have come up with the next topic, that is hydrocarbon. And I hope you have enjoyed my previous session. And if you have enjoyed, then you have to stay tuned with me till last minute. And the thing is, one more thing I want to say. In the description box there will be available of the freebie, that is the complete free hydrocarbon notes, and you have to stay tuned with me till last moment, then you can get it easily. So the thing that before starting my hydrocarbons concept, I have to wait for 1 to 2 minutes, so just let me wait for 1 to 2 minutes so that students can join me. So someone has joined. Sneha, yes, hello. And Logarthan, yeah, hello. I hope you are halfway to your revision series, right? So, all of you, how are you? I hope you are revising it very well because NEET exam is coming soon, right? Yeah. Hello, Mohammed. All right. So, students, you have to join me if you want to revise the hydrocarbon chapter completely. And no doubt, I am not feel you make it means I will not make you feel boring. Just let's make it interesting time. Okay. So, coming to the hydrocarbon chapter, so all over, what do you know exactly about the hydrocarbon? So, the hydrocarbon is what? The mainly the compound which is containing carbon and hydrogen all over, right? So the hydrocarbons can be either saturated also, unsaturated also, aromatic also. So aromatic in the sense what, where you will be having all over benzene ring. All right. Now saturated and unsaturated difference. What you can see, the saturated one where the carbon carbon single bond and the carbon hydrogen single bond, you can see the compounds which are having carbon carbon single bond and carbon carbon hydrogen. Apart from that, unsaturated where the carbon carbon with double bond, you can see, right? So the compounds which are containing carbon carbon double bond or the multiple bonds, we can say unsaturated hydrocarbons. All right. So now in case of hydrocarbon chapter, the important subtopics what you have to revise is, the first thing is alkanes, alkenes, alkynes, whatever you have. So these all alkanes, alkenes, alkynes, their nomenclature part, properties, preparation, isomerism. Okay, the preparation part is most important in alkanes, alkenes, alkynes. You have to stress on it more, more. Okay, so I'm just putting star mark. All right. Now, in case of alkanes, also you have to stress more on the conformations, because in NEET chemistry, PYQs, if you refer, so the conformation part where you will be having so many questions. So the conformations, better you know how to convert the molecules into Newman projections and all. All right. Now, coming to the aromatic hydrocarbon chapter, I am going to deal today. And aromatic hydrocarbons where the nomenclature, structure, properties, resonance stability, aromaticity, and isomerism, and their preparation, and specifically the properties when it comes with respect to chemical or else physical properties you are going to study, and specifically chemical properties where the electrophilic substitution reactions. So right, so PYQs of NEET chemistry, if you refer, you can have so many questions on these electrophilic substitution reactions, along with that the aromaticity concepts also, right? So now we'll start with aromatic hydrocarbons. All right. So, what are aromatic hydrocarbons? Aromatic hydrocarbons are those which are containing benzene ring, right? So, the compounds which are containing benzene ring in the molecule, we call them aromatic hydrocarbons. And you can see the examples here. The simple benzene you can see. Apart from that, toluene, where the benzene ring is containing single substituent, that is methyl group, and ethyl benzene, where the benzene is containing ethyl group all over. All right. So like that, there are so many functional groups which are attached on benzene also, like if you consider carboxylic acid which is attached to benzene, we call it as benzoic acid, right? So this is what benzoic acid we have. So like that, any compound which is containing benzene in a molecule, we call them aromatic hydrocarbons. All right. So now you have to know regarding exact structure of benzene, how exactly it is represented. So the benzene can be represented in cyclic manner, right? So we represent it like this, benzene with one ring inside it, right? So just we show the circle in a ring, cyclic ring. So now before representing this structure, so all over, so the carbon-carbon framework, how exactly it is made in the benzene, that you have to know. So in case of benzene, there are six carbon atoms. Okay, six carbon atoms. So each carbon atoms are attached to hydrogen atom, hydrogen atom. Along with that, all the carbon atoms are sp2 hybridized here. Okay, so all the carbon atoms in the benzene are sp2 hybridized, in the sense where one sigma bond. So if I consider this a sigma bond, apart from that, the pz orbitals which are empty, those are involved in the pi bond formation. So this is what the pi bond you can see all over in the benzene ring. So here the Kekulé has given two structures with respect to benzene, the resonance hybrid we can say, in which a molecule or the compound which can be in two forms. Like suppose we consider this benzene ring where you can see the pi bond placement inside the ring. So here it is there. All right. And in case of this structure, you can see it is quietly different. So only the thing you are going to concentrate mainly on electron distribution inside the ring, that is important. That's why the Kekulé has derived two structures, or the resonance hybrid we can say overall. That's why the resonance concept has come. And because of that reason, because of this resonance reason, the benzene is stable and compared to all molecules. So now coming back to its structure. So each carbon is sp2 hybridized. Okay, sp2 hybridized, and where it is having pi bond also. That pi bond is mainly where, how exactly it is formed, it is sideway overlap. So the sideway overlap of the sp2 hybrid orbitals of each carbon giving me pi bond inside the benzene ring. And each pi bond, whatever you can see, those pz orbitals are perpendicular to the plane of these atoms overall, and the sigma bonds are completely different. So each pi bonds are parallel to each other but perpendicular to the plane of the atoms. So this is what overall regarding benzene structure. Benzene structure you can see with respect to their pi bond formation and the sigma bond formation. Apart from that, the carbon hydrogen bond angle in the benzene ring is 120 degree, and the carbon carbon bond length is 1.39 angstrom, and the carbon hydrogen bond length is 1.09 angstrom. All right. So now this carbon which is attached to hydrogen, where the carbon is sp2 hybridized and it is forming bond, that is sigma bond with hydrogen, which is sp2s orbital. All right. So this is what structure regarding benzene. And now we have to go on study with respect to its stability and resonance part. So why this resonance concept has come? Why? Because we can represent benzene as its resonance hybrid also. So a single molecule can be shown in two different ways, where just you have to show the pi bond inside the ring differently. Like you can see this benzene ring and this benzene ring, right? So just all over you are concentrating on the electron distribution inside the ring. That's why these pi bonds, whatever you can see, are being shown differently with respect to their positions, and we can say they are resonance hybrid. So mainly it is first derived by Kekulé, and he has given its resonance hybrid structure. And this resonance hybrid structure concept has arisen. Why? Because the pi electrons which are present inside the ring are involved in the delocalization. So delocalization in the sense what the pi electrons are moving inside the ring, right? So it is what a ring current we can say. So all over. So here you can see in this benzene. Okay. So 1, 2, 3, 4, 5, 6 already it is numbered. So the carbon So from second carbon to third carbon, where the pi bond is being shown, all right, then first carbon, sixth carbon, fifth carbon, and fourth carbon. Right. And similarly, in the second resonance hybrid structure, you can see where between 1 and 2, 3 and 4, and 5 and 6. Right. So, like that, the pi bond formation inside, where it is mainly representing the electron density inside the ring, how it is distributed all over. And this is what the electron cloud you can see whenever you can try to imagine the electron density inside the ring. So, this is what, because of this resonance concept, the benzene is more stable compared to all other molecules, right? And here, when the resonance concept has arisen, and similarly, the benzene ring has the aromaticity property. So that you have to know what exactly aromaticity. All right. So what exactly aromaticity, and what are the criteria it has to attain in order to show the aromaticity property. So first thing, if a molecule, if we consider the benzene ring, or any molecule if we consider, if it has to be aromatic, then what we can say, it should have four criterias. Along with these three, there is one more criteria, that is, firstly, so just I will mention it as, so fourth one, so fourth one, where it has to be what? It has to be cyclic compound. First criteria. It has to be cyclic, then only we can say it can exhibit the aromaticity property. And secondly, it should show planarity. So the molecule has to be planar. Suppose you consider benzene, it is flat molecule. So it has to be flat molecule in order to show aromaticity property. Apart from that, the next criteria or the characteristic we can say, it should have the complete delocalization of the pi electrons inside the ring. So all over the electrons, whatever you can see inside the ring, those must be involved in the complete delocalization. That's what the second criteria. And the third one, the presence of 4n plus 2 pi electrons in the ring where n is an integer, and this is what we can say Huckel's rule. So it should obey Huckel's rule according to the aromaticity property. So first four criteria, what? Firstly, it has to it should have cyclic structure, all right. And nextly, it should be planar, in the sense it has to be flat molecule. And nextly, the complete delocalization of the electrons has to be there inside the ring. And fourth one, it has to obey Huckel's rule. So main four characteristic or the criterias it is following, then we can say that benzene ring or any other molecule is aromatic in nature. Now I have given three examples. Okay, so three examples, whatever you can say. Firstly, it is cyclopentadienyl anion. So whenever the molecule is being given, you have to concentrate more on the pi electrons in the given molecule. So now in the cyclopentadienyl, you have two pi bonds. So each pi bond will contribute two electrons, right? So now two pi bonds in the sense what? Two in the sense it will be four pi electrons you have. All right. So you have four pi electrons. Apart from that, on the ring, you have negative charge also. So you have negative charge also, and you have to consider the negative charge also. That's why by considering this negative charge, now it will be each negative charge again two electrons. All right. So it will be 6 pi electrons overall. Then I can say cyclopentadienyl is having 6 pi electrons and it is aromatic in nature. And in general, whenever you consider the molecule, if it has to show aromaticity, then it should have either 2, 6, then 10, 14, 18, and so on. So it should have 2, 6, 10, 14, 18, and so on pi electrons in it. Then we can say it can exhibit aromaticity. All right. Apart from this, any 1, 3, 5, okay, and 8, 4. So these all are what? Non-aromatic in nature. Suppose you consider cyclobutadiene as an example. So cyclobutadiene, where inside the cyclobutane, two pi bonds will be there. All right. So how many bonds you have? Two pi bonds, in the sense four pi electrons. So four pi electrons, then it is anti-aromatic, so that it is not aromatic, that overall we can say. All right, so if it is having 2, 6, 10, 14, 18 so on electrons, then we can say it is aromatic in nature. Now coming to the second example, in benzene it has 6 pi electrons in it. If it has 6 pi electrons, then we can say it is aromatic in nature. And in case of naphthalene, this is naphthalene, right? So third compound is naphthalene, where it is having how many electrons? So 5 pi bonds you have. So 5 pi bonds, in the sense all over it has to be 10 pi electrons. So 5 pi bonds, 10 pi electrons, then it can obey Huckel's rule and it is aromatic in nature. So, like that, the aromaticity of a molecule, whenever you are checking, so you have to concentrate firstly on the pi bond. So, you have to look at the pi bonds, how many pi bonds are present in a molecule, and then only you can say whether it is aromatic or non aromatic. All right. So, don't stress on this n value in case of Huckel's rule. Instead of that, go for the pi bonds in the given molecule, and then you can calculate according to the all over how many electrons are present, then you can say whether it is 2, 6, 10, 14, 18, within that range. If it is coming, then you can say it is aromatic in nature. So these are what all examples all over I have given. And students, if you have any doubt regarding this, you can ask me. So just let me look at. Yes. Okay, so if you have any doubt, you can ask me in the chat box so that I can answer you. Now, coming to the next part is problems. You have to solve problems now. So, the question is like this. In pyrrole, they have given the structure of pyrrole. This is the structure of pyrrole. In pyrrole, the electron density is maximum on. So, on which position the electron density is more, that you have to tell me. So, if you want to answer this question, then you should know how to write the resonating structures of pyrrole. Then only you can answer me. So just try to do what answer you can give, students. So just let me know. Yes. So just tell me that in the given pyrrole structure, on what position the electron density will be more. So I have given 4 options: 2 and 3, 3 and 4, 2 and 4, and 2 and 5. So try to solve this question based on writing the resonating structures of the pyrrole. So Sneha is answering it is B. What about others? Okay, so let me show with the resonating structures here. Okay, so for resonating structures of pyrrole, how you can show? So firstly, these lone pair of electrons, whatever present on the nitrogen, are donated. Okay, so it will be like, so first these electrons donated here, and now this bond is shifting here. All right. So how you can show? You can show the structure like this. So the ring as it is nitrogen, which is carrying one proton, and here the new bond is formed, and now nitrogen is carrying positive charge all over. The remaining pi bond I am keeping as it is, but the thing here, the bond you have shifted and it has to attain negative charge. And now overall you have to shift the bond, you have to shift this bond here, okay, and this bond here. Okay, so it has to be shown here, and then where the nitrogen, which is carrying proton one side, and pi bond here. All right, and here positive charge, and here this is what shifted bond you have. Apart from that, the negative charge you can show here. And nextly, again you have to shift the bond in such a way that, okay, so now it will be shifted all over once again here. So now the ring which is carrying charges, that you have to concentrate more over. So now you can see double bond here, and again nitrogen is carrying positive charge. Apart from that, this carbon is negatively charged and this bond is as it is. All right. So now again what I can show all over. So this double bond will be shifted here, this again here. Okay, and this negative charge here, so you can get your pyrrole back. Only the thing, if you consider its resonating structures, okay, and the charge separation, if you consider all over, you can see on second, if I consider numbering 1, 2, 3, 4, 5. Right. So on second and fifth carbon, you can see charges here. This is fifth carbon charge, you can see, right? And here in the second. So this is what the second position, and here the fifth position. You can see the charges overall. And these two structures are more stable compared to remaining all resonating structures. And that's why what we can say in pyrrole, the electron density will be maximum on second and fifth position of the carbon. Okay, so by considering resonating structures, we concluded that the charge or the electron density overall, if you look at here, the second and fifth one is mainly preferred where the electron density is more and it is giving more stable structure. And that's why I can say these two structures are more stable structures. Apart from that, you can answer like by comparing the charge separation also. So when you consider the charge separation, so whenever the charge separation is more, suppose you consider in this second one, where the nitrogen which is carrying positive charge and the carbon, third carbon is carrying negative charge. So overall, where the charge separation is more, and then what I can say, the stability will be reducing. Okay, the stability will be reducing. And that's why whenever you look at the carbon and nitrogen or else any other substituents, overall you can check if the charge separation is less, then I can say the stability of the molecule will be more. Okay, so in the given options, the option D will be correct one, where the second and fifth position which is carrying more electron density compared to 2, 3 and 3 and 4. Okay, so now coming to the next question is benzene do not show one of these two options in the given option. So option A, where it is delocalization of the pi electrons, and B, greater stability, C, resonance, and option D is electrophilic additions. So in the given criteria also, in the starting whatever you have studied till now, so there you have not you where you are not familiar with the delocalization or else its stability or else with the electrophilic addition, so that you have to check on. So what answer you can give me, students? Okay, Logerton says it is option D, and Stunner says it is C. Okay, Chinmay, yeah, hello, very good evening, I'm fine, and what about you? Yeah, Sneha is answering as it is option D. Yes. So the option is D only here. Very good, students. So the option D is correct here. Why? Because obviously we know that benzene has the delocalization thing inside in its ring, right? So the delocalization of the pi electrons, and because of that reason, what we can say, it has so many properties. And secondly, it has greater stability because of the resonance. And third option is resonance itself. Yes, obviously it has. And the electrophilic addition, the benzene will not undergo electrophilic additions easily, rather than it will undergo electrophilic substitutions easily. That in case of chemical properties, you are going to study in detail. All right. So now we'll move on further with respect to the remaining part of aromatic hydrocarbon, that is preparation method. How well you can prepare the benzene. There are so many preparation methods for the benzene, but the thing is, so many. So I have mentioned three preparation method. So first thing is cyclic polymerization method. So in case of cyclic polymerization method, the 3 moles of ethane is being considered, and it is passed through the red hot iron tube, and where the temperature is about 873 Kelvin is maintained, and you are getting your benzene. All right. So what you're doing, just you're doing the cyclic polymerization of the 3 molecules of these 3 moles of ethynes you have. All right. So these 3 molecules or 3 moles of the ethynes are combining each other through cyclic polymerization. Just you're passing in red hot iron tube, and you're maintaining 873 Kelvin, and you're getting benzene as a main product. And this is one preparation method in case of cyclic in case of benzene preparation. And now coming to the next preparation method is decarboxylation of aromatic acids. So in case of carboxylic acid, we know that it can undergo decarboxylation easily, right? So when you have sodium salts of benzoic acid, so sodium salts of benzoic acid, whenever you are treating with sodium hydroxide, which is base, upon heating in the presence of calcium oxide, you are getting your benzene along with the side product Na2CO3, sodium carbonate. Okay, so this is what another method where you can follow in order to prepare benzene. Apart from that, what and all method you have for your benzene preparation? And nextly, reduction of phenols. So just the reduction of phenols, whenever you consider, the phenols can be reduced in the presence of zinc. So the phenol vapors are mainly passed through the heated zinc just upon heating, and you will get benzene as a product along with zinc oxide will come out. So this is what the reduction of phenols, where by reducing phenols you are getting benzene. Apart from this, is there any method to follow to prepare benzene? Yes, there is one more method also, that is by considering diazonium salts. So if you have N2 plus and Cl minus, okay, so just you are treating in the presence of H3PO2 in water, you will get benzene as a product. So there are so many methods for the benzene preparation, but few preparation methods I have mentioned. And now we'll move on further with respect to its properties. So what and all the properties we do have, the physical and chemical properties. So physical properties where the aromatic hydrocarbons are immiscible with water. Why they are immiscible with water? Because we know that the organic compounds are non-polar in nature, right? So aromatic hydrocarbons are non-polar in nature, and they are not they are immiscible with water, and but are readily miscible with organic solvents like chloroform and all, CCl4, carbon tetrachloride. So so those many organic solvents are there, so there it will be miscible. And now they burn with sooty flame. Okay, so they burn with sooty flame. Why they burn with sooty flame? Because they are containing cyclic rings. So whenever you try to burn the cyclic rings, they will not burn completely. That's why it will give sooty flame whenever they are burning. Apart from that, the chemical properties, where chemical properties, it can undergo, as I have told, substitution reaction, that is electrophilic substitution, addition reaction, and oxidation reactions. So now we'll start with the chemical preparation, that is chemical properties of benzene. What and all the reactions you can follow for the chemical reactivity. So now coming to the first method is nitration. So as I have told, the electrophilic substitution reaction, the benzene is nucleophilic in nature, or else it is electron rich center, because electron density is more in the benzene ring. So now coming to the first method is nitration. So in case of nitration, what you have to do, you have to take benzene and treat with concentrated HNO3 along with concentrated H2SO4 by maintaining 323 to 333 Kelvin, and you will get NO2 substituted benzene, that is nitrobenzene you will get. So now you have to see how exactly the mechanism is followed in case of nitration of the benzene. So firstly, what happens, you will be having your HNO3. So you will be having HNO3, and HNO3 will be receiving one more proton from acidic media, that is H2SO4. So now you have your H2SO4, and where oxygen is bonding to hydrogen, right? So now here what happens, the oxygen which is carrying lone pair of electron, it will grab the proton from the acidic media, and after grabbing, you can see that oxygen here overall it is carrying negative charge, and this side oxygen which is carrying two protons on it and which is carrying positive charge, right? So oxygen will not keep itself quiet because it is carrying positive charge. So now what it will do, so just I will show here, this is positive charge. So once it carries positive charge, now what it will do, it will try to go out as water molecule. So it will go as a water molecule and you can generate your electrophile, that is NO2. So now H2 has gone out, shift these electrons towards this bond, NO2 plus you have, right? So you have NO2 plus and where it is carrying positive charge. So now what you have to do all over, so you have to attack this NO2 plus on benzene ring. So just I will consider benzene ring which is carrying pi bond inside it. So now you have your electrophile, right? So you have electrophile. Now these pi electrons will be attacked on electrophile, that is NO2 plus, and now you can see benzene with two pi bonds along with that NO2. Apart from that, the carbon where you are attacking, we know that each carbon is carrying one hydrogen, right? So now on this carbon also there is one hydrogen, and whatever here after attack of electrophile, so here one more carbocation is generated. Along with that, this overall we call it as a sigma complex, right? So we call it as a sigma complex or else arenium ion we can say. So this sigma complex where it is carrying sp3 carbon. We know that inside the ring all the carbons are sp2 hybridized. You are converting sp2 hybridized carbon into sp3 carbon, and this is what overall we can say sigma complex. So this sigma complex, next what it will do, it will lose its one proton. So that proton how you will remove, so you have to remove that proton whatever in the first step where the electrophile you wanted to generate in the presence of H2SO4. So one of the proton was grabbed by the oxygen which was containing lone pair of electron, right? So where apart from that electrophile generation, the HSO4 minus was left as it is. So that HSO4 minus, now it will come back and it will attack on the proton and it will grab the proton out. Okay, so it will grab the proton out and you will get, so where it is going as H plus by lagging behind the electrons, right? So now where you can see benzene along with double bond and here you have your NO2. So this is what the nitration product of benzene, where you are substituting NO2 plus electrophile on benzene ring. So this is what nitrobenzene you have. So one more thing you have to observe here, that sigma complex whatever you have got, it has to be stabilized by resonance, right? So now you have your sigma complex, how you can stabilize. So here you have your benzene ring and where just I will show here how exactly the charge is stabilized inside the ring. So now you have, okay, so here you have your NO2 and here you have your hydrogen. All right. So now it has to be stabilized. So this charge has to be stabilized. So what you can do here, you have to shift this bond here and then you can see all over the ring as it is, and where it is carrying NO2 and one hydrogen is left as it is on the carbon, and here this double bond you can see. So this charge is satisfied now. So this charge is satisfied. Then again one more charge, that is carbon, which is bearing positive charge once again. So next what you can do, again you can satisfy this charge by shifting these electrons here, and you can see here the new bond here. All right, so here double bond you have and NO2, one side hydrogen you have, and this bond is shifted here, right? So now this carbon will be bearing positive charge, so I will show like this. So like this the charge whatever you can see in the sigma complex is stabilized by resonance. That's why the benzene ring, whenever we consider the aromatic hydrocarbons, are more stable. Why? Because whatever the charge is bearing on the ring has to be stabilized by the resonance. So that's what you can see. This is how the sigma complex is stabilized overall. So this is what the mechanism regarding nitration of electrophilic substitution reaction. Now coming to the next part is halogenation. So apart from nitration, the electrophilic substitution reaction, what you can say, it is halogenation, where the halogen like Cl2, Br2 are mainly preferred on the substitution with benzene ring. So now what you have to do, you have benzene ring which will be treated with Cl2 in anhydrous AlCl3. So anhydrous AlCl3 is a Lewis acid where you are mainly using it in order to generate electrophile. So every electrophilic substitution reaction first starts with what? It starts with generation of electrophile. So once you generate electrophile, then it will be attacked by benzene ring. So right now you have anhydrous AlCl3. So in the presence of anhydrous AlCl3, it will generate electrophile. It will be substituted on benzene ring where you are getting chlorobenzene as a product. So now let's look at its mechanism also, how exactly you can write it. So now coming to the mechanism part. So firstly you have Cl2 and you are treating with AlCl3, right? So Cl2 you can split like this: Cl, positive part, partial, negative part. All right. So partial positive part and negative part, if you can see, AlCl3 will be taking one of the chlorine, and where the Cl plus will be generated along with AlCl4 minus. So overall, where AlCl3 and AlCl3 will be grabbing one chlorine out, and Cl plus is what? It is my electrophile. And now I'm ready with electrophile. Now what you have to do? You have to attack on benzene ring. So you take benzene as it is. So just consider Cl plus where it is carrying positive charge and these electrons are shifting towards electrophilic center, right? So now you can see benzene which is carrying two bonds along with chlorine which is already attacked on the ring, and you have one hydrogen here, right? So next what step you have to do? You have to stabilize this carbon which is carrying positive charge. So now cleave this bond, hydrogen will be going out. So here AlCl4 minus will be attacking. So AlCl4 will be attacking where it will release one of the chlorine, and that chlorine will grab this proton, and it will go out as HCl. So just I will write it like here HCl, and AlCl3 you have got as it is. Right. So now this H that is proton is going out with chlorine as HCl, and where you can see double bond as it is, and chlorine is already present on the ring. All right. So this is what overall you can see. You can see with respect to chlorination or else halogenation of the benzene, that is electrophilic substitution reaction. Another example. So now coming to next electrophilic substitution reaction, that is sulfonation. So in case of sulfonation, where the fuming sulfuric acid is mainly used here. The fuming sulfuric acid is just nothing but concentrated concentrated this concentrated sulfuric acid along with SO3. We call it as fuming sulfuric acid. So the SO3 gas is mainly preferred for the sulfonation, but it is inactive. Just to activate the SO3 gas, sulfuric acid is mainly preferred, and it is activating SO3, and it will then convert it to SO3H, then that will be attacked by nucleophile, that is benzene. So now just let us look at its mechanism, how exactly you can follow. So in case of sulfonation, first what you have to do, you have to generate electrophile, right? So you have SO3 and H2SO4 you are using. So this H2SO4 overall OH you have. So now acid will release proton, right? So one of the oxygen will be grabbing this proton, right? So now what you can do, you can have SO3H, right? So SO3H where it is electrophile. Apart from that, you have your HSO4 minus, right? So you have everything as it is. Now this electrophile has to be attacked on benzene ring. So just I will consider benzene, and you have your SO3H, right? So you have SO3H in which it is mainly attacked by benzene, right? So you have SO3H, and again it will attack on this. So every step is followed one and same. So SO3H you have, and here again same carbon is bearing hydrogen, and here it is carrying positive charge, where so this hydrogen will go out again with this HSO4 minus as H2SO4, and it will give its electrons back to the bond where the ring aromaticity is retained, where benzene sulfonic acid as a product you are getting. So this is what overall sulfonation method with respect to electrophilic substitution reaction. Okay, so now coming to the next part is alkylation. So alkylation and acylation, that is Friedel-Crafts alkylation and acylations, are the two methods where we can give two more examples with respect to electrophilic substitution. Again, here you are using the source, that is alkyl halide, to alkylate the benzene. So benzene will be treated with alkyl halide where in the presence of anhydrous AlCl3, which is again Lewis acid, which is mainly useful in order to generate electrophile. So now what you will get? You will get ethyl benzene as a product. So now just let us look at its mechanism once again. Now coming to its mechanism part, where you will be having your alkyl halide. Okay, so alkyl halide, where so before that I have to generate what? Electrophile, right? So first you have to generate electrophile in such a way that, okay, so now you have your C2H5Cl, you have your C2H5Cl plus AlCl3 you have, right? So you will be having C2H5Cl and you will be having AlCl3, where AlCl3 will be going out as AlCl4 minus. Again, you have generated your carbocation or else electrophile, you can say. So electrophile is ready, C2H5 plus. So now you have to attack it on benzene, right? So just consider C2H5 plus. So here it will be attacking on it. Again, same step you have to follow where you are going to form sigma complex C2H5 you have and hydrogen. So this hydrogen again it will go out as HCl and AlCl4 again it is coming as it is HCl. I have written here. All right. So now what this hydrogen will go? So new bond will be formed and what I can say, that is ethyl benzene. Right. So this is what ethyl benzene you will get from alkylation, that is Friedel-Crafts alkylation method. So this is what overall with respect to Friedel-Crafts alkylation. Now coming to next part is Friedel-Crafts acylation. Instead of ethyl halide, you are using acetyl halide here. So now you have acyl groups, that is CH3CO, where this CH3CO, that is acetyl chloride, we can say it will be again attacked by benzene ring, and we that is also again followed in the presence of anhydrous AlCl3. So benzene is treated with acetyl chloride in the presence of AlCl3. Just upon heating you will get your acetophenone product. Okay, so that is what overall we can say acylated product also. So now coming to its mechanism once again. So you will be having acetyl chloride. All right. So you will be having acetyl chloride, and again it is treated with AlCl3. So where you will be generating CH3CO plus and AlCl4 minus. Right. So now benzene you have, again benzene will attack on electrophile, attack it. Again you are going to form sigma complex. All right. So you have CH3CO, right? So here it is carrying one hydrogen. Again, it will go out with chlorine, where you are getting your acetophenone as a product, right? So this is what Friedel-Crafts acylation product. So these are what the electrophilic substitution reactions you have followed. Apart from this, again it can undergo addition reaction also. So mainly in case of aromatic hydrocarbons, you should know electrophilic substitution reaction. Apart from that, it can undergo addition reaction also, but you are maintaining vigorous condition here. So now coming to its addition reaction specifically. So whenever you have benzene and you are treating with nickel where it is mainly hydrogenating agent. So here in the presence of nickel, it is giving me cyclohexane. So this is what the complete hydrogenation process. So this is complete hydrogenation process. Apart from that, partial hydrogenation also you can do, but here you will use sodium in liquid ammonia. Sodium in liquid ammonia if you use, then you can say the benzene can undergo partial hydrogenation. That is what. So benzene if you have, then treat with sodium in liquid ammonia, you will get benzene. So one of the pi bond will be hydrogenated. You will get the partially hydrogenated product. Apart from that, if you treat benzene with high excess of chlorine under UV light, and where you are maintaining 500 Kelvin temperature, you are getting BHC, that is 6 chloron atoms substituted cyclohexane you are getting. Okay, so this is what overall we can say addition reaction with respect to benzene. So if you maintain vigorous conditions, then definitely it can undergo addition reaction. So it will normally do not undergo addition reaction, but you have to maintain either any one of the condition. Okay, now coming to the combustion method where the benzene by heating in air, it will undergo combustion and it will produce carbon dioxide along with water. So this is what combustion method with respect to benzene. Okay. So now with this, we are about to end hydrocarbon part, that is aromatic hydrocarbon part. And now you have to solve with respect to their questions also. Before that, you have to know regarding their influence of functional groups which are present already on the ring. So in case of benzene ring, what happens sometimes? Suppose you have any benzene ring. So any substituent, if I consider X, so whatever the substituent is present on the benzene ring, it will be further guiding to the upcoming group to um, to go to any one of the position, either ortho, para, or meta. So that is what overall the behavior completely depending upon the substituent which is already present on the benzene ring. So you know that the electron donating groups and electron withdrawing groups. All right. So in case of benzene, whenever the benzene is carrying electron donating groups or electron withdrawing groups which is already present on the ring, it will guide either ortho and para position selectively or else meta position selectively. So that you have to know. So just let us look at it. Okay, then we'll solve few problems. So coming to ortho and para directing groups. Whenever you have electron donating groups on benzene ring, we know that what are electron donating groups? They will always increase the electron density on the benzene ring, right? So now you have OH. So OH is what? Electron donating group. So this OH, what it will do? The oxygen which is carrying lone pair of electron, it will donate the electron to the benzene ring. So once it donates, again delocalization you can see here in the first structure overall. So once the electrons are involved in the delocalization, so negative charge is generated on the second carbon. Apart from that, again it will shift towards the next carbon. Again it will shift simultaneously. You can see overall resonating structures with respect to phenol. So the resonating structures, if you observe carefully, at second position, fourth position, and sixth position. Okay. So on benzene, if you consider, if you have OH. So on second position, fourth position, and sixth position, the electron density is more. If electron density is more, then what you can say, the electrophile which is incoming, it can attack easily, and the faster the reaction it can follow. All right. So you have to conclude one thing, that whenever you have electron donating groups, they are ortho para directing groups. In the sense, the upcoming electrophile can attack to either second position, fourth position, or sixth position of the benzene ring. So this is what regarding orthopara directing with respect to EDG. Now, halogens also can act as orthopara directing groups, but the thing is the minus I effect. What exactly the minus I effect? We know that all the halogen atoms are most electronegative, right? So they are always ready to push the electron towards them. If they're pushing the electron towards them, then the next adjacent carbon will be bearing partial positive charge. In the sense, the electron density will be reduced all over in the ring, right? So in case of any aromatic hydrocarbon which is bearing halogens, there will be some kind of moderate deactivation with respect to ortho and para directing nature. So now in case of chlorine, if you consider where the lone pair of electrons which are present on the chlorine are involved in ring donation, so they are donating electron towards the ring, and that's why it is carrying at 2, 4 and 6 carbon negative charge, so that electrophile can come and attack. But apart from that, what I have stressed, the minus I effect of chlorine, that is halogens, are mainly moderately deactivating the group. Okay, so any activating group which directs the electrophile to ortho and para position, that is mainly with respect to electron donating groups. All right. So now coming to next thing, that is meta directing group. So what exactly we do have with respect to meta directing groups? So now if you have electron donating groups, you concluded that yes, the upcoming electrophile can go and attack to the ortho and para position. So it is guiding to ortho and para position. Now, if you have electron withdrawing group overall on the ring, then where exactly it will guide? So it will guide in such a way that if you look at the resonating structures of benzene ring here, so in case of benzene ring, so overall NO2 is electron withdrawing group. It has to withdraw electron towards itself, right? So it is withdrawing electron density towards itself, then the benzene ring will be electron deficient. Now if you check with respect to its resonating structures, where we are shifting the benzene pi bond towards nitrogen, so overall you can see here nitrogen is bearing positive charge, and apart from that the adjacent carbon is carrying positive charge. So this is second carbon, right? So now in the third structure, you can see again the fourth carbon is bearing positive charge. So just you're shifting the pi bond inside the ring, and overall at 2, 4, 6 position, the carbon is bearing positive charge. Then at meta position, so this is what the meta position you have. So these meta positions are free, where it is not bearing any positive charge. In the sense, what it is having more electron density compared to ortho and para positions, right? So because of that reason, what you can say, the meta directing groups are always electron withdrawing groups, which will direct the incoming electrophile to meta position, and they will deactivate the ring. Okay, so they are deactivating groups overall, we can see. So any deactivating group which directs the electrophile to meta position. So this you have to keep in your mind. So now with this, I am ending this aromatic hydrocarbons, and now you have to solve few problems with respect to um, this aromatic hydrocarbon chapter. And this is what overall I have given the examples with respect to activators and deactivators. So activators where EDGs you have to conclude, and deactivators where EWGs you have where exactly they will guide to meta position, and EDG where they will guide to ortho and para position. So you have so many examples here: NH2, NHR, NHR2, OR, OH. So these all are electron donating groups which are guiding to the upcoming electrophile to ortho and para positions. Now coming to the deactivators, where I have mentioned deactivators which are moderately deactivating, not completely, moderately deactivating groups, that is all halogens, and strongly deactivating groups you can see overall. So here the example I have given with respect to halogenation of ethyl benzene, where ethyl group is what? Electron donating group. Then Br2 is halogen. So upcoming electrophile you have. Now what you have to do? The attack has to be either ortho position and para position. So it is mainly guiding the upcoming electrophile to either ortho and para position preferably. Now in the second example, you have CH3CO as a substituent on the benzene ring, which is electron withdrawing group, which is mainly guiding the upcoming or the incoming electrophile to the meta position. So this is what the meta major product you are getting. So these are what the examples I have represented in a single table. So just go and refer it. I hope I have completed the important part of aromatic hydrocarbon, students. So if you want anything, then you can you can ask me. So someone is asking Tapas Das, what is EWG and EDG? So EDG and EWG is just shortcut forms of electron donating groups and electron withdrawing groups. So EDG is electron donating groups. Okay, and EWG is electron withdrawing group. So just I'm showing here. So electron withdrawing group. All right. So electron withdrawing group, they withdraw electron. Electron donating groups, they donate electrons, like right hand and left hand type. Okay. So now, so this is what with respect to overall aromatic hydrocarbon chapter. Okay. Then if you have any doubt, you can ask me, or else we'll start to solve the problems. Okay, so now we'll start with the problem session. So first question is like this: the benzene reacts with methyl chloride in the presence of anhydrous AlCl3 to form. So benzene is reacting with methyl chloride in the presence of anhydrous AlCl3. So what product you will get, students? So options are xylene, toluene, chlorobenzene, benzyl chloride you have. So what options you can choose? Okay, Logarthan is asking what just differentiate between electrophile and nucleophile. All right. So electrophile is electron deficient atom. Okay. Nucleophile is nucleophilic, that is electron rich source we can see. So that is what we can differentiate. Electrophile is electron deficient. Nucleophile is electron rich. Okay. So Sneha answering B. Logarthan is answering it is C. Okay. So just let us look at the reaction. So what they have given? Methyl chloride. Okay. They have given methyl chloride and they are treating with benzene in the presence of anhydrous AlCl3. So now you have benzene and you are treating with methyl chloride, that is CH3 plus and Cl minus, you can split, right? So CH3 plus is what? Electrophile. So if it is electrophile, then benzene will attack on it, right? So this is what? Friedel-Crafts alkylation, right? So you have to get toluene as a product. So here in the given examples, xylene is where? So xylene is where it is like this type of compound. So where the benzene ring is carrying two methyl groups, this is orthoxylene, like that. Ortho, meta, para xylenes are there. So only xylene is mentioned. So the xylene is not possible because only CH3Cl you have. Then toluene is the answer where C6H5CH3 is you are getting. So nextly, chlorobenzene is not possible. Yes, here the Cl is not attacking. The methyl group you are going to attack as a electrophile. And benzyl chloride, where how you can represent benzyl chloride, that is C6H5CH2 Cl, right? So you are not attacking CH2Cl. So just you are attacking methyl part to the benzene as a electrophilic substitution reaction, that is Friedel-Crafts alkylation. So whenever alkyl halide along with the anhydrous AlCl3 is being mentioned, then you have to think that yes, it is Friedel-Crafts alkylation. Then you have to mark the answer where it is having the alkylated product. Okay. So now coming to the next question. So just look at the question properly. Among the following reaction that proceeds through an electrophilic substitution reaction is. So four options are being given. Just look at the reaction properly and the products what exactly and the reactant what you're reacting with the benzene and the product you are getting. So just look at it and let me know the answer what you can say. Yes, students. So answer fastly what answer you can get. So just think that in the option A, suppose you have benzyl alcohol you have, right? And you are treating with HCl. So I'm just giving one hint how you can approach the question. So you have benzyl alcohol with HCl. So how you can split HCl? You can split it like H plus and Cl minus, right? So now H plus where it will not attack. So Cl minus you have, right? So H plus where it will go along with OH and it will be going out as water molecule where CH2 Cl you are getting as a product. So what you are substituting there, Cl minus you are adding. So overall this is not electrophilic, this is nucleophilic, right? So Cl is nucleophile you are attacking, that's why you cannot say that is electrophilic substitution. So like that you can approach the remaining questions and which one you are replacing. So just let me know the answer what you can get. All right. So the answer I will say now. Okay. So first thing we confirm the option A, which is not electrophilic substitution, right? So here it is where the Cl minus you are attacking and water is going out. So this is also not possible. Now coming to the second reaction where diazonium chloride you have and the Cu2Cl2 you have. So directly chlorine is substituted, right? So here even here it is not electrophilic substitution reaction. Now, coming to the third reaction, just by closing your eyes, you can say that the benzene is treated with Cl2 in the presence of AlCl3, right? So, anhydrous AlCl3 you are using and you are getting chlorobenzene. Just now we solved that. What it is, this is where halogenation type of reaction, right? So, now this is what electrophilic type of reaction, electrophilic substitution we can say, right? So, option C is correct one. What about option D? Option D, where you are doing Cl2 addition. This is addition type of reaction. This is also not possible. So right now, what answer you have got? You have got the option C as correct one. Okay. So now coming to the next question, that is, which of the following can be used as the halide component for Friedel-Crafts reaction? If you know Friedel-Crafts reaction, then you can directly answer me. And just you have to correct one thing here. This is not chloroethane. This is chloroethene. Chloroethene. Okay, and this is not ethane, ethene. Just correct that. So just let me know answer what you can give me. Yes, Neha, it's okay. So Sneha is answering it is A. Okay, what about others? Okay, so the answer I'm going to tell you now. So first thing, what they're asking, they're asking regarding the halide component. So they're asking regarding the halide component, which will undergo easily Friedel-Crafts reaction, right? So Friedel-Crafts reaction, what we use alkyl halide as a reactant part along with benzene, right? So if you consider chlorobenzene, so breaking this bond is very difficult because even though if you break the bond, after that whatever the carbocation you are generating here, this is not stable, right? Now, so chlorobenzene is also not possible. In case of bromobenzene, just you are substituting the chlorine by bromine, and even this is the reason is one and same. So breaking bond, that is carbon halogen bond, is difficult. And now chloroethene they have given. So chloroethene where CH double bond CH2Cl if you consider. Okay. So here one hydrogen will be there. So CHCl it will be. Okay. So here this bond if you break, after that whatever the carbocation you are generating here, this is not stable one. Okay, so because of that reason, what I can say, even the chloroethene is also not a proper answer. If you consider isopropyl chloride, so whenever you can check for the carbocation stability with respect to saturated one and unsaturated. So overall, the alkyl groups, whatever the alkyl carbocation we can say, those are more stable, right? So now isopropyl alcohol, isopropyl chloride, if you consider, it will be CH3 twice CHCl. So if you break this, you are getting CH3 twice, that is CH3 twice carbon, which is carrying positive charge, which is more stable compared to all carbocations, right? So option D has to be correct here. Okay, so now coming to the next question is, what products are formed when the following compound is treated with Br2 in the presence of FeBr3? So this is another halogenation type of reaction where here you are doing bromination. Already on the benzene you have what? You have already two substituents. Okay, so metaxylene they have given everywhere. Only the thing Br you are going to attack. Now you have to tell me where exactly you can add the bromine here. So where exactly you can substitute the bromine on given reactant. So this is what the reactant you have. So just try to answer me what you can say. So just concentrate on Br where exactly you can attack. So here you have to concentrate on the position, along with that the steric effect also. So one hint I can give here, stress on steric effect also, because you are attacking bromine here. Okay, Logarthan is answering A and Sneha is answering it is 4. Okay, let's see. So in the given reactant, what you have? You have, this is your reactant. Okay, so you have your reactant and you are treating with FeBr3, right? So you're treating with FeBr3, and what you are attacking bromine, right? So after attacking bromine, so you can attack either here or else here or else here, right? So you can attack either here ortho positions or else para positions, right? So now in the given all options you have to check the bromine, as already I have told, it is where bulkier atom you have and you are attacking, and you have to concentrate on steric effect also. In the given option A you can see the bromine is between two methyl groups, right? So here there will be steric effect. Now the option A itself, where one more structure they have given, and option first structure itself is wrong, then you cannot go for the second one also. So option A is also wrong. Now option B, again you can see here the Br is in between two methyl groups against steric effect. So again option B is wrong. Now coming to option C, you can see bromine how frequent it is away from two methyl groups, right? So here you can see it is free of steric effect, and here also it is free. So I can say option C is correct one. And now option D again, where you can see they have shown the bromine attack here, right? So bromine will not attack here. It will attack either this position, or this position, right? So this is what the answer option C has to be given for this question. So now coming to the next question is, among the following compounds, the one that is most reactive towards electrophilic nitration is. So towards electrophilic nitration, now you have to tell me in the given options which one will be more reactive. Okay, so benzoic acid, nitrobenzene, toluene and benzene are being given. You have to compare with respect to what? The electrophilicity of the given options, and sorry, with respect to what? The nucleophilicity. So overall you know electron donating groups and electron withdrawing groups, whatever you have attached, based on that the electrophile will come and attack, right? So now you have to tell me what answer you can give with respect to this question, either benzoic acid, nitrobenzene, toluene, benzene. So you have to consider the substituents which all are present on the benzene and their nature, whether it is electron donating groups or else electron withdrawing group. Okay, how it will affect the incoming electrophile. So which one will be most reactive? So one thing we confirm that the ring has to be more electron rich, than the electron deficient center it will come and approach easily, right? So now what you can say, so Sneha is answering it is C. All right. So just let us look at the solution. Okay. So now you can see you have firstly benzene with carboxylic acid. So what is carboxylic acid? This is EWG, right? So we know that EWG will reduce the electron density on the ring, and we can say it is electron deficient, right? So it will not undergo electrophilic substitution more favorably rather than the electron donating groups attached to benzene rings, right? So now this is cancelled. Option A. Now coming to option B, where you have nitrobenzene. Yes, obviously again nitrobenzene, where it is carrying nitro group. So nitro group, again electron withdrawing group, again it will reduce the electron density and it will not undergo electrophilic nitration easily. All right. So now toluene you have, right? So toluene where you have benzene with CH3. And one more option what you have simple benzene. So simple benzene, obviously it will undergo electrophilic nitration, but the thing is you have to compare between toluene and benzene. So toluene where methyl groups you can see here, it is what electron donating group. If it is electron donating group, then it is increasing the electron density on the ring. Then I can say it is nucleophilic source, where it is electron rich source we can say, and the electrophile will be attacked, right? So now, so we can say toluene is more preferably undergoing electrophilic nitration rather than benzene. So when we compare between toluene and benzene, toluene has to be preferred first over benzene, so that I can answer option C is correct. Okay, so this is what with respect to aromatic hydrocarbons. We have solved so many questions and we have learned so many things. I hope I have covered important part of aromatic hydrocarbon. Okay, and finally, thank you. You have stayed tuned with, you have this moment you were there with me, and again I will come up with the next one more chemistry topic. And already in the beginning I have told you that in the description box everything that is regarding hydrocarbon, the free notes is available, and if you are there till with me, then you can download it. Until that, thank you, bye bye.